right, it's all up to you now. You're going to do some work. So I want to know what the weak shockwave angle is for a wedge of 12-degree deflection in a Mach 3 flow. Pardon? Right. So here's our vehicle. It's travelling off basically towards the left-hand side, or in a wind tunnel effect. The flow is coming from the left and going over the vehicle. The leading edge is here at the left and trailing edge at the right. The way that we draw these things, are these strong lines here are the actual shock wave. So there's two at the front and there's two at the back. These funny things here are meant to denote that it's expansion. The actual flow, as it's managed to get into region 2, when it gets to region 3, it's actually got more room than it had before. So what we've got up here is a 12-degree half angle, so 12 degree and 12 degree. So in other words, horizontal, 0 degrees here we're actually flying along. From the horizontal upwards, that wedge is 12 degrees. The free stream speed that we're travelling at is Mach 3. I want to know what the angle is from the horizontal up to the thick shockwave angle, shall we say, at the leading edge. Everyone ready? Yay, good. So what you're trying to do is find the parabola which says 3 on it, which is actually, there's part of it there and there's part of it there, sort of goes slight off. So there's one part round about there and one part up there. And then I want you to find, this is 12 degrees deflection to the horizontal. I want you to find 12 and work your way up. You find on the slides I actually sort of put red so that I can actually find where they intersect, like this. So there's the 12, draw a straight line right the way up for me. And then I found where the 3 is. Now, why haven't I bothered with the top one? Because the question said find the weak shockwave. So there's my Mach 3 parabola. Now, they intersect at that point there. And so I reckon it's somewhere around about, what, 29 degrees in that sense? Officially? Okay, 29 degrees. Okay, has everyone got that? Is that okay? Yeah? Lots of nods? Yeah? No shakes? No one having good few yawns so we can go a bit faster? Right, okay. Anyone doesn't get it, you can always shout. They'll get a bit longer as it goes. So, okay, answer's 29 degrees. So let's see how you do on number 2. What's the weak and the strong shockwave angles? Now you've got a wedge of 4 degrees and it is Mach 1.7. So basically, be careful of the questions when we say 4-degree deflection. Make sure if you see a picture of an actual wing, as you saw before, diamond wing, make sure you're sure what the angle deflected from the horizontal is up to the top of that vehicle. So 4-degree deflection, Mach 1.7, both the weak and the strong shockwave angle. Right, what do we think? We're getting there? Still going? Ish? Alright, let's see if you agree then. I reckon the bottom one is 40 degrees and the top one is 87. That'll do, that's close enough, 87, 86 will do. Alright, so if you're with it on this one, let's go to number 3. So, back to a diamond aerofoil, so in other words a wing, it's at Mach 2.4, half angle, deflection angle is 8 degrees, so we're still going straight along, 0 degree angle of attack, so the deflection is 8 degrees, Mach 2.4, what's the maximum wedge angle for which an attached shock can be produced? Slightly different this one. So okay, we're starting at 8, but that's actually a little bit of a red herring here. So if we look at 8, does 8 degrees actually cut into the Mach 2.4 line? Great, if it does, keep on going. There's a wedge angle of 12, 20, 24. Where is it that we get to a point where the Mach 2.4 doesn't work anymore? Somewhere around about 30 or something like that. So in other words, where's that curve of the parabola? Whereas if you keep pushing the wedge angle, you actually miss the curve completely. So what it should be, let's see what it says. It's around about 29 degrees. Okay, so after 29 degrees, you can't connect with Mach 2.4 parabola at all. Alright. So in other words, there's my 2.4 line there. And basically, if I'm here or here or here, I can cut into that line. But if I choose a deflection angle out here, I can't cut into 2.4, it's too big. So somewhere around 28, 29 degrees, I can no longer hit that line. So, we've got a diamond aerofoil 16 degrees. What's the minimum Mach number that an attached shock can be produced? 16 degrees. So in other words, it'll probably cut into 2.4. But, so what we're looking for is we're looking at 16 degrees here. And what we want to know is, if we go back a little bit, 16 degrees. So we can cut into all of these lines. So let's see, that's Mach 3, Mach 2 there. I can still cut into, I can't cut into 1.5 or 1.6 or 1. I just missed the whole thing. So therefore, interestingly enough on there, is that you can see there's a limitation for a half angle of 16 degrees. You can find an attached shock at some Mach numbers, but not others. It's just too much for, say, Mach 1.6. And then basically, if we're at Mach 1.6, we're going to get a detached shock wave. Right. So, we've got a diamond aerofoil. It's got a half angle of 16 degrees. Tell me about the strong shocks on this, that go from supersonic to subsonic. 16 degrees, work your way up. Let's see. 16 degrees, now where are you going to? So, what does the question actually mean? It means the following. There's 16 down here on the x-axis, and if I follow it up, all of this is weak shock wave, attached, 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 and it's all basically weak until I get to this one here, this line, the top horizontal line. After that, it's guaranteed to be subsonic flow. So anything above that line there, whatever that angle is there, will actually be subsonic flow after the shock. And to be honest, although these are classified on the bottom line between these two horizontal lines as weak shock waves, they also end up as subsonic flow as well. So you're looking for 16, follow it up really until you actually reach that top horizontal line and read across to beta. And if I show you that one there, it says above 65 degrees you're guaranteed to have a strong shock wave and it's subsonic. Between about 61 to 65 they're technically called weak shock waves, but again you actually produce subsonic flow between that barrier, those two little sort of horizontal lines. Now, something different. So we've got a wing, looks like a diamond. it's got a half angle of 8 degrees, but this time it's an angle of attack of 4 degrees. What's the deflection angle on the upper and lower surfaces? Well, basically, it's now at, I suppose I could even do that. So, if I actually tilt the wing up by 4, just see the angle drops for the deflection. So this is the upper surface of my wing, and I then say, right, angle of attack, you can see to the horizontal, the upper surface will start to drop. So that means the lower surface will start to increase. So 8 degrees, upper surface, 4 degrees angle of attack. So basically 8 minus 4 becomes 12. 8 degrees on the bottom, this is going to be increased by what? 4 degrees angle of attack. So that one's going to become 12. So when you do the calculations now, on that particular axis there, the x-axis, the fact it's an 8 degree half angle is not what is actually used here. What would be used is 4 degrees deflection to find out what the shockwave angle was on the upper surface, and 12 degree deflection to find out what the shockwave was on the bottom surface. Diamond aerofoil, 8 degrees angle of attack. Again, it's a bit of a busy wing, this one. Now, we put it to an angle of attack of 8 degrees. So, what's the deflection angle on the upper surface? Gets less. 8 minus 8, 0. Lower surface, 8 plus 8, 16. So, what's the shockwave structure? How many shockwaves have I now got? At the front, I started with 2. The previous question, I had started with 2, if you like, 0 degrees, went to 4 degrees, still had 2. Start here, 0 degrees, and then I deflected by 8 degrees. What would happen to it? Upper surface now, we said, was 0. So therefore, the flow coming along here doesn't actually have a shockwave at all at the upper surface. The bottom surface, it's got stronger. Now it's a 16 degree effect that it's actually suffering from. But if you go along that particular sort of upper surface of the wing, and your deflection, your angle of attack is the same, then basically you have actually removed the shockwave, which is what people often think about whether in future they could actually remove the shockwave from, say, the bottom surface of a supersonic vehicle by the way it was actually deflected in flight, so that there was no shockwave which actually went down to the ground and caused a sonic boom. Difficult to do. Okay, so I think for the moment that is round about where we are. Okay. So the last thing in this way is, what is it that you've actually got? It's about 2 minutes left. On the back of this. On the back of this is what's called a Prandtl-Meyer function table. You can imagine that this is the opposite. If the front is for shocks, compression, the back is going to be for expansion. And therefore, when we've got a surface of a vehicle and the surface drops away and the flow can actually spread out, this is going to tell us how it's going to spread out. What it's got is it's got a Mach number and it's got an angle. So therefore, if you can work out the angle that you've actually given extra to the flow, it'll start to tell you how your Mach, your speed, is actually going to increase as a result of that geometric change. Right.